Okay, so here's an example of how to find a Maclaurin polynomial. So firstly, what's a Maclaurin polynomial? So it's a Taylor polynomial that's centered at a equals 0. So it just means exactly Maclaurin polynomials and Taylor polynomials are exactly the same thing. This is just centered at 0. So I'm going to look at the function y equals cosine x here. So f of x is cos x, a cosine function. And so how does your calculator know how to calculate cos x? Well, it's by converting into exactly the thing that I'm about to convert it into here now. Now I've written that I want the Maclaurin polynomial of degree n equals 2k here. And that's because I'm going to employ a certain little trick and change my indices such that I can write this thing down neatly. So what do we need to calculate a Maclaurin polynomial or any kind of Taylor polynomial is we need derivatives. So f of x is equal to cosine x, and I need to differentiate this a few times. I need the nth degree nth derivative of this function. So we need to remember our differentiation rules, but they're not going to get any more complicated than this. In this course, and I'll just differentiate this a few times. So sine x differentiates to give cos x. So minus sine x differentiates to give minus cosine x. The third derivative of this, negative cos x, is going to go back to positive sine x. And sine differentiates to give, that's the fourth derivative, sine differentiates to give cos. So we're back to where we started. Right, so actually, this cycle goes around and around and around again. So the fourth derivative of cosine x is the same as f of x itself. Right, so that is actually equal to that. And the fifth derivative will just be the same as the first, the sixth the same as the second, and so on and so forth. So what's that? So that's the first piece of the puzzle, the derivatives. Now, why do we calculate those derivatives? Well, it's because we need to evaluate them at my center here. Right, so the Maclaurin polynomial means the center is at a equals 0. So cosine of 0, that's equal to 1. So the cosine function crosses through the y-axis at y equals 1. And then I need to do f prime of 0, f double prime of 0, f triple prime of 0. I need to keep going. I know this one already because the fourth derivative is the same as the original function. Okay, so negative sine of x, sine of 0 is equal to 0. The sine function goes through the origin. Cosine of 0 is equal to 1, so the second derivative here is negative 1. And the third derivative is going to be 0 again because sine of 0 is 0. So there's a nice pattern here actually. So as I differentiate and evaluate this function at a equals 0, at x equals 0, then I get 1, 0, negative 1, 0, 1, 0, negative 1, 0, etc., etc., etc. So actually only every second term is going to be non-zero in this polynomial. So that's interesting. I mean, that's actually related to this trick up here. And we'll see what we get. Okay, so now we actually have everything that we need. I want to evaluate this thing at any value of x. So let's write out what the Maclaurin polynomial actually looks like. So it's f of 0 plus f prime of 0 divided by 1 times x plus f double prime of 0 over 2 factorial, that's just 2, times x squared plus the third derivative over 3 factorial x cubed plus dot 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 dot. So I'm just going to get bored, so we'll put dot 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 dots in. And then I'm going to have the nth derivative divided by n factorial multiplied by x to the power of n. And obviously that's evaluated at x equals 0 there. And so now, this is actually just a matter of plugging numbers in. So f of 0 is equal to 1 plus I'm going to have 0 times x there, right? Plus negative 1 over 2 times x squared plus 0 times x cubed. I could keep doing this pattern here. So the next term would be 1 over 4 factorial times x to the 4. And then the next term is going to be 0 again, right? Because every second term here has got a 0 in it, and etc., etc. Right, and so the nth derivative here is f of n evaluated at 0 over n factorial x to the power of n. And now actually it's just a matter of tidying this all up. So here we have 1 take away x squared over 2 factorial plus x to the 4 over 4 factorial. Maybe you can start to see the pattern. Actually, the fifth term disappears, but the power of 6 term here ends up having a negative sign in front of it because of this sequence here. And I've got x to the 6 divided by 6 factorial. The next term would be x to the 8 over 8 factorial plus dot, 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 dot. And then I'm left with this term here. Oh no. X to the n. Oh, I ran out of space a little bit there, but that's okay. Now let me do something a tiny bit more to tidy this up. So maybe you can see, now you can start to see the pattern with the pluses and minuses, right? So here actually I can simplify maybe I won't get too cute and I'll skip out the x to the 8 term. You can start to see the pattern with the minus, plus, minus, plus, minus, plus here. And so what we actually have is negative 1 to the power of, something that alternates along here. Right, so that's where I actually put in negative 1 to the k, where k actually counts up every second term here. So that gives me, that's that term there actually. I get x to the power of n, and I've said that n is equal to 2k. So this is x to the 2k divided by n factorial, which is 2k factorial. So that my exclamation point has dropped off the bottom of the slide there a little bit, but that's the idea. So this is a whole game of doing pattern matching, of finding patterns actually. So every second term drops out, which means that all I'm left with are even numbers in the power. And then you start to spot the pattern goes negative, positive, negative, positive. And how do you generate a string of negative, positive alternating numbers? The usual trick there is negative 1 to the power of k. So whenever k is even, right, so every second term is positive here, and every odd numbered k, right, so all of those ones gets a negative value, and that generates every term in this polynomial. And actually, so whenever your calculator evaluates cosine x for some value of x, it doesn't know what cos x is. It doesn't know what that special function is. It can only do polynomial operations. It can only add and subtract and divide and multiply. And so actually it's converting cosine x into a long expansion like this. And that's how it actually works.